Alright, welcome to Engineering 270, Lecture 1. So in this lecture we're going to go over the basics of the processing system that we're going to be working with, which is called the Pic Processor. We're going to talk a little bit about what we mean by a microprocessor, where this kind of fits in to the hierarchy of things we're used to dealing with in terms of computers. And this is just going to be kind of an overview of the general course. So what is a microprocessor? Well, let's start by looking at a hierarchy of how we use computers. So at the top level, we've got applications. Okay, this might be a game, it might be a web browser, it might be a database interface of some sort, but it's the way that we interact with the physical hardware. Type in this box, hit this button, and so on and so forth. Those applications are usually written in some kind of high-level language. So an HLL, high-level language, could be C, could be Java, or something else. We'll think about C in this course. And C involves statements like if x is bigger than y, z equals 5 times the square root of x, right? Fairly close to how we're actually thinking about algorithms, but nothing that a computer can actually deal with, because computers understand something much simpler. They understand ones and zeros, what we call machine code. And machine code is what's actually executed by the hardware. So how do we get from C to machine code? Well, we go through a process called compiling, which turns C into something called assembly language. And then we can take that assembly language and run that through something called an assembler to get machine code. So assembly language is something like movef 23, W. Okay, it's still kind of human readable, but it's a far stretch from a high-level language statement, right? It's these small pieces, but assembly language translates pretty much one-to-one to the machine code that the hardware actually understands. So we're taking our complex high-level instructions and breaking them down into small pieces that the CPU can actually process. And this is going to be an important thing to keep in mind in this course. Anytime you want to do something like this, it's going to take you dozens, maybe hundreds of assembly language instructions to do this. Even something simple like take these two numbers and add them together is going to take you a number of assembly language instructions. And until you sort of accept that as your fate, you're going to be continually frustrated in trying to work with assembly language. And in this course, we're pretty much staying at this part of the hierarchy. We'll do a little bit of looking at C and how it translates to assembly, but most of our work is going to be writing assembly language code, translating it into machine code, or looking at machine code, translating it into assembly, and working with the actual hardware, hooking it up to switches, LEDs, things like that, and then making this all work together. So we'll write programs in assembly, turn them into machine code, put that into the hardware, and have the hardware interact with the outside world. So that's our basic setup for this course. Well, what kind of processor are we going to be using? There's a lot of different processors out there. Now, why are there so many processors? Why isn't there just one microprocessor everybody uses? And the answer to that is if you were to try to design sort of the ideal microprocessor, you might come up with the following criteria. You might like something that's very fast, also very inexpensive, very low power, easy to use, reliable, physically small, lots of I/O so we can interact with many devices, easy to update so when the physicists give us new transistors that are better, we can make a new version of our processor using those new transistors. So our ideal processor would optimize each of these criteria. The problem is what one of my professors called the n-way teeter-totter problem, which is once you optimize one of these, you're probably de-optimizing one or more of the others. For example, the faster your processor, usually the more power it takes, right? The cheaper your processor, probably the slower it is. A processor that is very small is not going to physically be able to accommodate a lot of I/O devices. Or if it does, if you can find ways to use more I/O devices by maybe using your connection points in different ways, that's going to slow down your software. And so there's no such thing as a single processor that does the best possible job in all these criteria. You have to pick and choose. What do we want to do with this processor? Do we need it to be very fast because it's going to be crunching numbers in some mission critical operation? Do we need it to be very cheap because we want people to buy these things? Do we want it to be very low power because it's going in a smartwatch? And so on and so forth. So the processor we're working with is made by Microchip and is called a Pic 18F1220. And that's one particular type of processor, but Microchip makes hundreds of different Pic processors, each tailored for different kinds of criteria. So this is the one that we're working with. Now, like every chip that we work with in Engineering 250, there's a data sheet to go with each of these processors. The data sheet for the Pic processor is over 300 pages long. And you're going to work with that a fair amount, and you're going to get to know a lot of that data sheet. But to get things started on Canvas, you can download a roughly 20-page extract of 20 pages that I've found to be the ones that you'll probably go to most in working with this processor. So you can download that from Canvas, and I'll give you a hard copy of it in class also. And here's the first page of that download. And it shows the pinout for the chip, but there's 3 pictures of the chip here. An 18-pin dual inline package, a 20-pin package, and a 28-pin, which is a quad flat pack. We're going to be working with the 18-pin, so this is the only pinout we're going to care about. And the first thing you'll notice is that this looks a little different from, say, a 74LS04, where our inputs were labeled A1 or X2. There's lots of labels on these pins, okay? So VSS is ground, pin 5 is ground, pin 14 VDD, that's power. So ground and power go on 5 and 14, that's not too hard. But if we look at some of these other pins, for example, pin 1, RA0, AN0, it's got 2 possible functions. Pin 15 could be oscillator 2, clock out, or RA6, that's got 3 possible functions. Pin 12 has 1, 2, 3, 4, 5, 6 possible functions. So what we're going to have to do when we use this chip is specify what do we want pin 1 to do, what do we want pin 12 to do, what do we want pin 15 to do, right? Other than the power and ground on 14 and 5, we're going to have to generally specify what we want to do with any pins that we plan to use with our program. So we're going to have to condition this chip, we're going to have to specify how it is that we plan to use it. All right, so that's going to be another sort of complication that we have to deal with. And why is this? Why do these pins have 2 or 3 or 6 different functions? Well, because a Pic processor has a phenomenal amount of capability inside. So if we just come down here and we look at the second page, we start to see some of the details. There's timing circuitry, there's oscillator circuitry, there's in-circuit debugging. There's a series of timers, there's an analog to digital converter, there's a way to do universal synchronous asynchronous reception transmission, so-called EUSART, CCP, so communication systems. So we can do a lot of different things with this one 18-pin chip, and the data sheet has 20-some chapters, with each chapter describing basically a different subsystem inside this device. So all of this stuff is sitting inside this one chip, and we've only got 18 pins, 16 if you don't count power, to interact with all of this. So we need to multiplex these pins. We need to have a pin that can do multiple different things. Okay, so that's going to be something to keep in mind. So what are some of the features of the Pic processor? Well, it has 18 pins. So 18 pins, 5 volts power. We can power it with other voltages, but it will work fine with 5 volts. So the same way we've been powering other chips works fine with the Pic processor. Memory-wise, it's got approximately 2K of memory, and we'll have to specify exactly what we mean by that, but not a lot of memory, but plenty of memory for the kinds of things we're going to do, okay? But forget about gigabytes, forget about megabytes, a couple of K, okay, 2,000 memory locations. It can do input and output. It can read and write ones and zeros with things outside of the chip itself. It can also do analog input. It can read a varying voltage coming in anywhere from 0 to say 5 volts and turn that into a digital number that represents that voltage. So we can sample analog things. It can do something called pulse width modulation, which we can basically use to control things like motors and make them run at a variable speed. It has an advanced universal synchronous asynchronous receiver transmitter. This is a way to do serial communication. It has timers, so we can set it up and say, hey, after 17 seconds, I want you to do something. And then we can go off somewhere else in our code, and 17 seconds later, this thing that we asked to happen will happen. It has a series of interrupts, ways to say, hey, if somebody pushes this button, I don't care what you're doing, I want you to respond to it in the following way. And we don't have to check to see if a button is pressed. We can arm an interrupt that will fire when this button is pressed. So we'll spend a lot of time talking about interrupts. It has a variety of options for oscillators. It can use an internal system to generate the main system clock, or we can also supply external clocks. So a lot of variability like that. All right, so that's the end of lecture 1. That's a very high-level overview of microprocessors and the Pic processor itself. Lecture 2, we're going to give a high-level overview of the main software we'll be using, and we'll start talking a little bit about assembly language.